Okay, great. Well, it's my pleasure to introduce Professor Duncan Callaway from University of California, Berkeley. And today he's going to be talking about uh, the grid of the future and some cutting edge modeling we're doing on that. So he has a talk called Exploring Future Power System Stability. And he's going to be talking about the role of power electronics in this next generation of grids. All right, a quick bio about Duncan. So he's an associate professor of energy and resources at Berkeley. He's also a faculty affiliate in their electrical engineering and computer science department, and also a faculty scientist at Lawrence Berkeley Lab. He did his PhD work at Cornell University and also held engineering positions in industry. And so he teaches courses on electric power systems, as well as statistical learning and energy. All right, Duncan, I'll let you take it from here. Thanks.
Thanks, Brian. Just a quick thumbs up from folks to make sure you can hear me and see the slides, or tell me if not. Okay, great. All right, thanks everybody for joining. It's a real pleasure to be here. Unfortunately, I haven't been able to join your other seminars this quarter, but it's been a really terrific lineup of people in the power system space, power engineering, and I'm really honored to be in this group. So today I want to talk about some work that that I've been doing, very collaborative work with a number of different groups to examine power system stability in the future, as the title suggests. And I'll say that the beginning of this talk, at least, is something that I gave in a grid forming converter workshop at UW a few years ago. So some of you may have seen some of this work before, but there's hopefully something that will be interesting, some interesting tidbits toward the end. And I'll also have some time to go more slowly through the topics because I have a bit more time today. So without further ado, let me just start by setting the scene. I'm going to take a little bit of time doing this because I want to make sure that folks understand the significance of the challenges that we're talking about, and also maybe sharing some of the excitement that I have for what the future holds for electric power systems. So let me start by defining a term, or helping you understand a term that's used quite commonly in the power systems world these days. And a lot of people are talking about low inertia power systems. And maybe the easiest way to describe that is to first talk about how power systems are typically or conventionally configured. So if you think about it, most of our sources of electric power today, it comes from so-called rotating machines. So there's an image on the right here of a rotor from a so-called synchronous generator from a large nuclear power plant in Alabama. And you can get a sense just by looking at the people nearby how massive this machine is. And I want you to imagine that when that's working, it's running at 3,600 RPM, or to 60 hertz, 60 cycles per second frequency. So there's a lot of rotating mass in just that one machine. And now imagine across the entire continent, many of these things spinning to serve electric power to all the customers on the grid. So what's particularly remarkable about these rotors is that they have enormously powerful magnetic fields on board that spin at 60 hertz. Simultaneously, the current that's flowing through the so-called stator of these machines, the stationary part that's sending power out to the rest of the grid, also has its own magnetic field. And these two things interact with one another, and they couple the speed of that rotor quite rigidly to whatever the frequency is of the grid. So if it's typically 60 hertz, that rotor is going to be moving at exactly the same speed, except in very extreme circumstances. And so in this sense, we say that each machine's inertia is rigidly connected to the grid. And so if there is a disturbance in grid frequency, the inertia of all of these spinning rotors tends to smooth out those disturbances. So what do we mean then by low inertia? We're talking about a future system where we have much more of our supply coming from power electronic converters. So this is on the roadmap to decarbonizing our power systems, right? So if we want to get natural gas fire generators or coal fire generators offline, one of the most viable ways to do that is with wind turbines or photovoltaics, or buffering out the variability in those sources with energy storage. In each one of those cases, we're going to start using power electronic converters that no longer have this tremendously rigid connection to the grid that a rotating machine does. And in particular, you don't have that 3,600 RPM massive spinning device that can buffer out disturbances in the grid. So there's a lot of hand-wringing over the future of controlling frequency, among other things, in power systems when we have much less rotating mass. And instead, we're getting our electric power from these other kinds of devices. Just as an aside, when you think about a wind power plant, those, you think maybe, okay, there's the rotating turbine on the wind farm, or on the wind turbines, the rotating blades, but those are not rigidly connected in the same way that a rotor on a synchronous machine is. Instead, there's power electronics sitting in between. And I'll talk a little bit more about those power electronics in just a second. So as I suggested, there's all of this concern over the future of electric power system frequency, because we've got this 60 hertz rigid connection with synchronous machines and not with power electronic converters. But one of the questions that we're going to explore in today's talk is whether it's only frequency that we should be concerned about. Are there other kinds of state variables in the system that might be equally hard to control if we have a reduction in the amount of inertia on the system? So we're going to answer this question: what happens more generally with less inertia on the system for system stability? So what do I mean by stability? So there are a number of different ways that we can measure the performance of the grid with respect to its state variables and whether or not they're stable. So early grid scale work, and when I say grid scale, I mean something at the scale of like the Western Interconnection, where I am and where those of you that are viewing from Seattle are also. So this is a very large interconnected system that spans not quite an entire continent, but it goes thousands of miles north and south. So early scale work on these kinds of systems that were specifically asking questions about low inertia dynamics, focusing on things like the rate of change of frequency. So what you can see in this chart here on the right is a plot of the evolution of system frequency in a simulation versus time after a disturbance. So say you lose a big generator, frequency will decline because we convert the rotating mass of those inertia, of those spinning rotors, into electric power in order to make up for the loss of one generator. So there's a certain rate of change of that frequency, which is like this initial decline here. There's a nadir, or the minimum frequency that you might see in different situations. And then there's some steady state frequency that you arrive at after the disturbance is finally cleared. And so early scale work is focused on these kinds of dynamics. Some would call these Newtonian dynamics after Isaac Newton, because we're talking about the about kinetic energy and inertia and the kind of typical things that you would learn in a mechanics course. What's beginning to emerge, though, is other areas of concern, as I suggested on the last slide, is what I'll call higher order dynamics. And here now I'm going to start thinking specifically about stability in a more formal sense. So this actually is a chart taken on the left. The lower left is a plot taken from a paper that Brian Johnson, one of the professors in this department, was involved in a few years ago, where they asked the question, is a system with lots of low inertia generation small signal stable? So what I mean by small signal stability is, if you look over here on the right, we're looking at, you've probably seen these kinds of analogies before. Imagine you've got a ball that sits in a valley held down by gravity. This red ball and this blue ball are small signal stable in the sense that if you poke them, they're going to roll back down into the bottom of their valley. whereas that green ball is small signal unstable. If you give it a little nudge, it's going to move away from the place where it's at rest. So this question of small signal stability is actually what we're going to be addressing today. I also just want to highlight another important area that is also merits a lot of new investigation in this low inertia world, which is what we call transient stability. It won't be the topic of today's talk, but if you're interested in this space, I encourage you to learn more about this as well. So imagine you take that red ball, if you hit it hard enough, it might wind up going into where the blue ball sits, in which case that red ball's equilibrium point there is transiently unstable because you could move it out of its resting place into another resting spot. Okay, so before I go further, I want to give you just a crash course on inverter control, because these terms, GFL and GFM, are going to come up a lot in the talk today. So if we think about conventional inverters, so an inverter is that power electronic device that takes your PV farm or your battery storage and converts it into an AC waveform to use on the grid. This is what the overwhelming majority of inverters on our grids do today. We call these grid following, in a sense that they will lock onto grid frequency using a phase locked loop and then track that frequency exactly. They'll have set points for real and reactive power and just adjust their waveforms in order to deliver that real and reactive power, but tracking the frequency of the grid precisely. So in this way, you can imagine it wouldn't work without a grid connection. You need to be able to sense that grid frequency to decide what to do with your inverter. A grid forming inverter, on the other hand, has much more complexity in the control loops, where instead of sensing grid frequency and just following that exactly, it produces its own frequency set points, but then makes adjustments to that frequency in order to synchronize itself with the grid. It sounds like that might be the same, but that subtle difference means that you can actually regulate frequency with a grid forming converter. And as the name suggests, you can actually build up a grid without a connection to a larger synchronous grid. You can build up a grid with a collection of grid forming inverters. So a droop control example, and this is what we'll be studying in the talk today, is one in which suppose that frequency and voltage magnitude on the grid were to go down, or actually, yeah, then the real and reactive power on the system of the inverter would change in response. So, or actually the better way to say it would be, suppose that that power electronic converter is attempting to maintain some set points. As a consequence, real and reactive power change. When it senses that, the grid forming converter will then reduce its frequency and voltage in response. And so in that way, it's setting its own voltage magnitude and its own frequency. What's remarkable is that these devices can synchronize themselves. And so you can operate them essentially in parallel. And there's been a lot of really important work that's happened with regard to grid forming inverters around that question of synchronization. So if I put the grid following and grid forming converters head to head, if we compare what they can do, a grid following converter, which is what most of our devices are today, will instantaneously control real and reactive power and can basically guard themselves against fault currents. However, they cannot operate standalone, and you could never have a 100% grid following converter-based grid. Whereas a grid forming converter, on the other hand, instantaneously will balance loads without a centralized coordination. That is, they power share if you have many of them together. They can operate standalone, and they can achieve a 100% penetration grid. So the upshot then is that it's easy to think of a grid following converter just as like a negative load. If you're a power system operator, it's out there, you know pretty well what it's going to do. It's going to deliver some real and reactive power amount. It's not going to provide fault current to any large degree. Whereas a grid forming converter is our current solution to power sharing in the absence of a synchronous machine. So if we want to have 100% power electronic converter based grids, we need some amount of grid forming converters. There are a lot of exciting system level perspective reasons to be thinking about grid forming converters and a lot of interesting challenges to solve, and I'm going to talk about some of those today. So before I do, I want to actually highlight a paper that came out, I believe actually just last year, a really important scoping paper that laid out a roadmap for grid forming inverters. Brian Johnson was one of the authors, and so you can see the UW symbol down there. And they posed a number of really important questions. And these are actually, it turned out we were already addressing these questions when this roadmap came out. So I was really excited to see the roadmap, and they said in many regards some of the questions we're interested in, but more eloquently. So they asked questions like, can heterogeneous systems containing grid following, grid forming, and synchronous machines operate together to guarantee stability? Next question, what are the interactions between machine excitation systems, which I'll talk about a little bit more in just a moment, and inverters with either grid forming or grid following controls? And then third, just a statement, and we're going to explore this statement as well. Assumptions that underlie our current design and control approaches for the grid must at a minimum at least be re-examined or maybe even redefined. And so this is actually one of the places where I think this area is so exciting, because we have an opportunity to completely rethink the way that we model and design electric power systems as these grid forming converters come into the fold. So here are actually the specific questions that I'm going to address. So right now, I'm done now finally doing my motivation, and I'm going to outline 4 questions that I'm going to try to answer for you to varying degrees of detail as we go through the rest of the time today. So first question, are low inertia, large scale grids small signal stable? So low inertia meaning not much synchronous generation, large scale meaning modeling systems that are of the size of a large transmission scale grid, so spanning at least hundreds of miles. And the answer that we'll find is that actually not always. They're not always small signal stable. And we'll look at what factors appear to drive that destabilization. And so just to preview, what I'll show you is that there's actually important interactions between the control loops on the conventional synchronous machine and then those inverters themselves. Both grid forming and grid following inverters show some similarities here. Second question that I'm going to address is, do conventional power systems analysis modeling assumptions hold in these low inertia grids? And here again, the answer is not always. And we'll explore what are some of those assumptions that may no longer hold. And in particular, we'll find that conventional assumptions for the way you model a transmission line need to be re-examined. And in some cases, the way that you model a transmission line has quite profound and fundamental impacts on the assumptions that the conclusions that you might make about small signal stability for a large scale grid. Question 3, what can be done to influence the stability of these grids? So if we see that there are instabilities, what can we do to try to manipulate those instabilities to potentially restore stability? So I'm actually going to come at this at what might seem like a bit of a backwards way, but it's a kind of an artifact of the funding that we have right now for one project where we're focusing actually on adversarial kinds of actions. So I'll explore one situation where a bad actor in a grid might actually make a system less stable with eigenvalue and eigenvector placement strategies. But I'll offer some preliminary ideas for ways to actually make things better, to take those instabilities and to mitigate them and make a system stable. And then the fourth question that I'll answer, this is quite open, and it's really just kind of shameless self-promotion of some work that we're doing right now on computation, where I'll ask, what's the future of computation in power systems analysis? So what I'm going to show throughout this talk is that complexity really matters in these low inertia systems, much more than in traditional ones, because of overlapping timescales that we didn't have before in a conventional system. And I'll lay all of that out as we go through. And so then I'm going to describe to you very briefly a new simulation tool called Power Simulations Dynamics, or PSID. And I think it's an exciting path forward for potentially expanding the way that we do computation, specifically for thinking about power system dynamics. Okay, so question 1, are low inertia, large scale grids small signal stable? So this is work that was begun when I was at ETH Zurich on a sabbatical in 2018. And there's a lot of collaborative work here. The 2 lead people on the effort were Uroš Marković, up on the upper left there, and Ognjen Staniev in the middle on the top. Other collaborators were Vagelis Retos, Gabriela Hug, and Petros Aristidou. So I'm about to throw out a whole bunch of acronyms. So let me just define these really quickly. A voltage source converter, or VSC, think of that as the inverter. So these are the inverters that we're replacing low inertia or synchronous machines with. So SM then stands for synchronous machine, that 60 hertz rotating magnet. AVR is an automatic voltage regulator. I'll actually define this in a block diagram in a second. A power system stabilizer, also I'll show you in a block diagram, or PSS. And synchronous reference frame, another acronym that's going to show up when we're talking about converter control. Okay, so let me I just want to do a nod to prior work that's happened in this area. So when folks have thought about small signal stability with a mixture of synchronous machines and converters, some of the earliest work dates back to Reza Eravani and Phil Lane at Toronto back in 2007, where they were thinking about microgrids and exploring questions about synchronous machines and voltage source converters and stability. The focus there was really one on modeling and microgrids. So not asking specific questions about what are our thresholds of penetration of voltage source converters, but instead just trying to understand how should we be going about modeling in this microgrid context. Bob Lassiter at Wisconsin is one of the originators of this notion of a grid forming converter. And so this is my second big bullet here, has worked on intersections between voltage source converter design factors and stability. So with his PhD student Erickson, as well as Wei Du, who's a postdoc with Bob over the last several years, they've looked at a number of different questions around designing parameters in voltage source converter grid forming control loops to ensure stability. This work, it was certainly important to pave the way, but again, was a microgrid focus. So, think of like hundreds of kilowatts rather than thousands of megawatts of capacity. And also their focus was not so much on looking at limits to stability and penetration. So the one, I think perhaps one of the most similar papers, and this actually inspired some of the work that we did when I began in Zurich, was exploring the specific question about maximum penetration of voltage source converters. And this was Yashen Lin and others in a NAPS paper from 2017. They focused on small signal analysis with different levels of voltage source converter penetration. The focus was certainly large scale, but a number of things were left out, and some stuff that we wanted to try to add in. But this was one of the first papers where people said, look, actually there could be limits to the penetration of these different kinds of converters. In this case, they were looking at grid following, but there could be limits from a small signal stability perspective. So in this, what I want to talk to you now about is an approach where we're looking at models with grid forming, grid following, and synchronous machines, all located at different buses, and exploring specifically questions about network dynamics. So how does the model that we use for the transmission lines affect the kinds of conclusions that we can make? And there's going to be a lot of detail that you'll see in just a second in the way that we model these devices, because we'll show that those details turn out to matter in ways that we've been able to ignore in the past. So the approach is to take a differential algebraic equation modeling strategy and then do kind of standard linear systems analysis to compute eigenvalues and eigenvectors. And also something called a participation factor, which gives us an idea for how individual state variables in this system contribute to different levels of instability. And I'll show you a parametric analysis where we're looking at different ranges of grid forming and grid following converters, and also asking questions about network dynamics. Okay, so there's a lot of information in this model for what we use for a synchronous generator, and I just want to point out kind of the bigger picture issues. So first, if you look over here in the upper right, this is the physical device itself. So we have a 6th order model that describes the magnetic fields in the device, as well as the frequency and angle of that device, and it's connected to the grid. Everything else that's outside of that top right is describing, for the most part, just control loops that make this thing work the way we want it to. So traditionally, a synchronous machine will have a frequency control block. And so that's down here. And this is something that's just trying to get its power output to match whatever is needed on the grid to maintain a desired frequency set point. So we've got frequency control loops. We've got what's called an automatic voltage regulator. If you've studied generators, you've learned that if you adjust the magnetic field strength on your rotor, then you can adjust the voltage output of the device. And so this automatic voltage regulator is the thing that's trying to set what the grid coupled voltage is for that synchronous machine by adjusting its rotor magnetic field strength. And then finally, we've got this power system stabilizer block. So as we started layering more and more synchronous generators together in the last century, what folks found was that there were some large instabilities that could generate where one synchronous generator would essentially what's called swing against the other one, meaning that they would get to a point where they start to have these modes of oscillation that get bigger and bigger and bigger. And a power system stabilizer's purpose is to prevent those modes of oscillation from emerging. And so this is like a wrapper control loop that adjusts the torque that that generator provides to the grid in order to ensure that at least for some modes of instability, that synchronous generator is stable. And what we'll see is how that can kind of unravel as we add more and more grid forming or grid following converters. So yeah, now let me talk about these grid forming or grid following converters. We use a 2-level voltage source converter control model. So again, I want you just to think kind of at the high level. You don't have to look at every single state variable here, but let me begin as I did with the synchronous generator and talk about the physical device itself, right? So a power electronic converter takes a sequence of transistors or a bank of transistors and figures out how to open those and close those gates very, very, very quickly, such that it chops up a DC waveform coming from your battery or your photovoltaic device and turns it into an AC waveform. So we've got various kinds of controls that make that happen. The device level control is maintaining a voltage and a current to come out of that bank of power electronic devices. And then there's a system level control. If you're doing grid forming or grid following, it's in this block that those controls will get embedded. And so I'm going to be talking about device level control on voltage and current, as well as system level control on things like real and reactive power as we go forward. So let's go ahead and look at that in a slightly more detailed version of a voltage source converter model. So we use a 3-phase balance representation. So we assume everything is balanced. And here, now you can see in this blue area, we've got a system level control block. In this blue area here, we've got device level. And then over here, we've got the physics of the device itself. So once again, you can see voltage and current control, reactive and active power control sitting in these two sort of major blocks. And we're going to be asking questions about how do each one of those blocks contribute to instabilities when they arise. So we've got a different model for a grid following converter as well as a grid forming converter. The key difference here between the grid following and the grid forming is this phase locked loop. Remember I said before, a grid following converter has to be connected to the grid to work, and that's because it senses that grid frequency and then basically reproduces it. And this is what that phase locked loop does. Okay, so finally, before I do my final dive into getting into the results, the network model, I want to talk about this very briefly. So I'll show you some initial results with a very simple network, just 2 buses. We've got a power electronic converter on one bus, a synchronous generator on the other bus, and loads on both sides. And I'm going to explore first a situation where the model or the line between those buses is just what we call an algebraic representation, meaning that there's no dynamics in voltage or current on that line. We just take whatever is happening on one side and assume the same thing is happening on the other, mediated by some static impedance. So, but then we'll look at a case where we say, well, what if there are voltage and current dynamics on that line, and how does that change the conclusions that we make about stability? So first I'll show you results with a 2-bus system. A little bit later, I'm going to show you a 9-bus system where we're looking at the importance of network strength in mitigating instabilities. And then finally, just to throw out as much validation as we can for these kinds of results, I'll show you some results with a 59-bus Southeast Australia representation. So this will be a very large, now finally like continental scale transmission model. Okay, I want to pause. I want to take a second and talk about timescales in these different control blocks before I finally give you some results, because it's the timescales that really matter in the way that we've done power systems analysis to date, and in the way in which adding grid following or grid forming converters can change the conclusions that we make. So if you look on the x-axis here, we see questions, or we see sort of indications, demarcations of different timescales ranging from below 1 millisecond all the way up to tens of seconds on a logarithmic scale. So first I want you to focus on the top kind of 2 rows, the grid itself and then synchronous generators. This has been the world that we've lived in up to now, where you've got signal processing happening on very, very fast timescales. In the 1 to 10 millisecond range, we've got network line dynamics. And then in frequency dynamics, we've got other somewhat fast dynamics on voltage happening with the AVR and the PSS. Remember, AVR is getting your voltage where you want it with your synchronous generator, and the PSS is manipulating that voltage in order to ensure that you've got stability at the system level. And then we've also got flux dynamics within the synchronous generator, which actually could span over to much faster as well, but they kind of bump up all the way here into the kind of hundreds of milliseconds range for the time scale of oscillation. And then we've got frequency dynamics on the governor and the turbine, and then these so-called swing dynamics that I mentioned before. So before we look at the voltage source converters, you can see that, especially looking at networks, line dynamics versus all of these other dynamics, there's not much overlap in terms of those timescales. So historically, we've said for the purposes of thinking about stability of these systems, we're going to ignore those line dynamics and just focus on the dynamics of these other devices and their interactions between 2 devices. So now let's take a second and look here, though. We've got voltage source converters, capital F meaning grid forming, lowercase f meaning grid following. Here now, if we think about the timescales of these control loops, the DC side control, think about your battery DC voltage or your PV inverter or your PV panel DC voltage. And then the synchronous reference frame, inner control, this is on current and voltage. Those things happen in the 1 to tens of millisecond timescale, the same as our network line dynamics. So then the question becomes, do we need to start thinking about those network dynamics as we do our voltage or our small signal stability analyses, because we've got all of this overlap? But then you can see other kinds of timescales overlapping on the active power and reactive power control, as well as a phase lock loop. And those interact with a conventional control on our synchronous generators, or at least they appear at the same timescales. So there's lots of reasons to think that some gremlins might lurk in the system as we get more and more coupling between these different devices that have control loops happening on similar timescales. Here's an example, like first example of those gremlins lurking. So let me start by showing, let's look at the bottom figure first. So we're looking at the size of the largest real part of any of the eigenvalues in the system. So with this 2-bus system, we're looking at something, over 20 different state variables and eigenvalues associated with them. And so we're just picking off the largest of those eigenvalues and saying at what point does it become positive, which would imply a small signal instability in our system. And then on the x-axis, I'm plotting how much generation is coming from grid following converters. So the first example is synchronous machines and grid following converters. And so it's a little bit hard to see, but at 60% penetration, meaning that we have 40% of our generation left coming from synchronous machines, everything else coming, that 60% remaining coming from the grid following converters. At that point, the real part of that largest eigenvalue crosses over into the right half plane and we have an instability show up. And that real part gets larger and larger as we add more and more generation from the grid following converters. So this is consistent with some results that we've seen before, in particular that Lin et al. Paper that I mentioned, observing some instabilities. This is focusing right now on what we call algebraic network models. So we're not looking at line dynamics, but I'll show you in a moment how for this particular setting, the line dynamics don't change the result very much. We'll come back to that in a second. What's interesting here is just to ask the question of what dynamics are implicated in this destabilization event. And you can see that when now we're looking at the largest participation factors in our instability. So this is basically a quantitative way of saying which state variables play the biggest role in that instability as it evolves. And you can see here that it's the power system stabilizer, which is actually trying to stabilize the system in the first place, interacting with the inner control loops on voltage and current on the voltage source converter. Those two together are the ones that dominate the origination of this instability. But then as we add more and more power electronic converter generation, other devices begin to matter as well as the initial instabilities or the initial blocks in that time scale. So the automatic voltage regulator starts to matter as well. As we get more and more penetration, you see that frequency dynamics start to become important, and the phase lock loop also becomes implicated in these instabilities, as well as active power control. And then finally, these Newtonian swing dynamics on the synchronous generator. So when you get to very high penetration levels, all of these different control blocks matter. So as these things emerge, it's saying these matter in addition to the initial state variables in the instability. And what this implies is that there are potentially a lot of different state variables that we have to be concerned about in order to ensure the system is small signal stable if we want to guarantee that in the future. Really important point is that the inertia constant has no bearing. So even though we're saying this is a low inertia system, the amount of inertia is not the thing that's causing the instability. It's these other control loops that sit on board the voltage source converter acting with the other control loops that sit on the synchronous generator. Okay, so now let's talk about what happens if we add a synchronous machine, we add a grid forming converter. Remember, these are the ones that can actually form their own grid by regulating voltage and frequency themselves. In this case, we see that the systems are more stable, but ultimately the same factors will destabilize the system. In particular, if you look here, we see that it's those inner control loops on the grid forming converter interacting with the power system stabilizer that cause that first crossing over into the right half plane for that largest eigenvalue. Something important to note is that the swing dynamics, and because there's no phase lock loop on the grid forming converter, also the PLL dynamics, those are no longer something that emerge as an important source of the instability. Once again, I'll show you this in a second, the network dynamics don't change the result. Something very important though is that the unstable mode is pure real. So typically when a power systems analyst thinks about instabilities emerging, they think about unstable modes that are oscillatory, meaning that the eigenvalues have complex parts. In this case, we actually see that the unstable mode that's emerging is pure real, meaning that it's just a first order instability that would be potentially hard to observe by just looking at things like damping coefficients, which are what we normally try to pay attention to see if instabilities are happening on real systems. Okay, now let me talk about network dynamics. So network dynamics changed the story, especially for zero inertia systems. So how I want you to look at this chart, first, let's go ahead and just focus, if you can, on the grayed out lines here. So before looking at the more bolded, solid colored lines, look at the grayed out lines. And these are the stability margins, or the largest real part of any of the eigenvalues in this two-bus system that you would get if you assume that there are no dynamics on the network. And remember, that's our conventional assumption in power systems stability analysis. So if you look at the blue, this is for grid synchronous machine versus a grid following converter. And then the bold is showing what happens if we include the line dynamics. And you can see that still there's a slightly higher penetration acceptable for the grid following converters, but ultimately you do cross over into the right half plane for that largest eigenvalue. Very, very similar result with the grid forming converter. So here is that largest eigenvalue for the without the network dynamics, and then the bolded line here is the largest eigenvalue with the network dynamics, and it's an extremely similar result. Where the big difference comes in, and this is a result that I haven't shown you with or without network dynamics yet, is if you've got only grid forming and grid following converters, no synchronous machine. And so in this case, the penetration is saying how much of the system is grid following. So we begin with 100% grid forming system and then start adding grid following to the alternate bus. So without network dynamics, the system becomes unstable at about 60% penetration of the grid following converters. With network dynamics, we see no emergence of that instability happening. So in this case, the line dynamics really matter, especially for this 100% converter power electronic based system. And if you look at what are the participation factors, what are driving those instabilities, it's frequency related issues. So the line dynamics are essentially preventing the propagation of unstable frequency dynamics across the system. So there are other results. I should note that other papers have found that network dynamics can actually erode stability. And so this, among other things, I think, well, we looked at a different situation. So in this other work that found erosion of stability, they were looking at all grid forming converters in a much more complex network. In our case, we just had a 2-bus system with a grid forming converter at one and a grid following at the other. It's different enough that we can't say that one result is wrong and the other is right. But it does suggest that there's a lot more work to do to understand how network dynamics are what role they're gonna play going forward. Okay, so question one then, let me go back and hopefully convince you that I've got an answer, at least a partial answer to this. Are low inertia, large scale grids small signal stable? For the assumptions we've made so far, the answer is no, not at high penetrations, unless we are 100% low inertia, in which case we do see with line dynamics that we can have stable systems operating. And what's interesting here is that it's the interactions between the control blocks on the voltage source converters and the synchronous generators that produce that instability. So basically both the conventional systems and the new systems work against each other. Okay, so I'm gonna, now that I've got my main result out, I'm gonna start speeding up and going through some other kinds of basically like little sketches of results. So we looked at one case where we examined the same kinds of questions on a larger network model. And we asked the question, what happens if we add more network connections? So as we still have dynamics, but in this, on the lines, but in this case, we're saying scenario one, just these black lines in the model. Scenario two, we add the black lines plus red, so add some additional network connection. And scenario three, add even more network connection in the system. And what we find is that as you add network connections, the stability margins improve, although not markedly so. So let me just, in the interest of time, I'll focus on this one with the grid forming over here. So each one of these is telling us at what percentage of grid forming converters, as compared to synchronous generators, does the system become small signal stable? And you can see that as you add more network connections, that percentage gets higher and higher, but it's still there. There is still a threshold. So question two then that I posed at the beginning, do conventional power systems analysis modeling assumptions hold in low inertia grids? The answer here is that the transmission line models matter a lot, and in some cases in quite fundamental ways. So you might mischaracterize the point at which you have an instability arising, but even more extremely, you might actually say that a system could never be stable, as we did with the dynamic less transmission lines, versus a system that can be stable over a broad range of operating conditions. And this is for that specific case of the 100% power electronic converter grid. But I should say that there's so much more to investigate. So we haven't looked at the most detailed kinds of transmission line models that one might use, so-called distributed parameter models. They're essentially discretizations of, or even direct continuous in space partial differential equation models of the dynamics on those lines. Other questions about power electronic converter switching, can we continue to ignore that? We have done that so far. So this is something that happens on the sort of less than 1 millisecond time scale. My guess is that we can continue to ignore those switching dynamics, but it bears some investigation. Another question, are there circumstances in which we could ignore those inner control loops on a voltage source converter for modeling simplicity? Okay, so I'm about to show you, actually, you know what I'm going to do? Rather than give you a fire hose of results on the next slide, let me just set up the model that we investigated with the South Australia case and give you the main result, which is shown in a lot of detail on the next slide, and you can examine that in a paper if you want. So we looked at a system where we have now, instead of just 9 buses or 2 buses, what if we have 59 buses, a much larger scale transmission system? And we asked, basically, if we put the power electronic converters at different locations in the grid, how do these stability margins differ? And what we see is that the limits to stability depend on location. So changing your grid following converter location or even your grid forming converter location as the penetration increases can improve the margins of stability. So there are some places that basically that are more vulnerable than others to those stability margins. So you can get with this model, at least with the right placement, you can get very high penetrations of synchronous generators, or low penetrations rather, down even as low as 12% in our simulations, and still have a stable system. So I want to just talk quickly about a couple more questions in the last few minutes remaining. First, what could be done to influence the stability of these low inertia grids? So this is work done in collaboration with Kieran Roberts and Dan Arnold, who are the far left and far right of the pictures here, who are both at Lawrence Berkeley Lab. Kieran is also doing a PhD in ECE at Berkeley, and then Uroš Marković again from ETH Zurich. And as I suggested, we're going to explore one situation where an adversary could actually make things worse. And this is because some funding that we have at LBL from DOE is focused specifically on that question. But I'm going to offer some preliminary ideas for how to make things better. So the high-level question is, can we re-engineer device controls to improve stability margins or degrade stability margins? So the first setting, as I suggested, is a nefarious one. So suppose that somebody can plug an active load into a microgrid. So this is a smaller system, and we're imagining that scenario because it would be easier for one actor to actually have a large enough effect on a microgrid to potentially destabilize it. So the question is, could they destabilize the system with the right feedback controller on their active load? So if we have a microgrid that's originally stable with synchronous generators and grid forming or grid following converters, could that active load basically create an unstable mode with the right feedback controller? So we are actually inspired by some work that's over 20 years old now by a titan in the field, two actually, Chris DeMarco and Fernando Alvarado, who asked this question in the era of restructuring about whether you could get a synchronous generator to destabilize a system as something like an active power electronic load would in our case. And they laid out a very straightforward process for doing eigenvalue and eigenvector placement with some somewhat aggressive assumptions. So they assume that you can observe either directly or via something like a Kalman filter all the state variables in the system, and you're aware of the system model. But in that case, I'm not going to go into this detail because of time. It's pretty straightforward to go through the linear systems theory to design a feedback controller by which you can place any pair of eigenvalues anywhere in the complex plane that you want to put And so here's just some example results where we were looking at this case, which is slightly different from Krista Marco's from back in '96, where we wanted to know, what if we have lots of power electronic converters on this system rather than just synchronous generators? And what if it's a load that's trying to destabilize the system rather than a synchronous generator adjusting its own feedback controls? So we actually identified we explored two possible kinds of attacks. So in the first case, we said, well, what if we take the modes that are typical synchronous generator electromechanical instabilities? What if we start with a system that is small signal stable, but then design that feedback controller to place the eigenvalues of that small signal stable system over into the right half plane? Then we also looked at a case where you identify some new modes that are electromagnetic and originate from the fact that we've got power electronic converters on the grid. These are the modes here, and we say, okay, can we place those over into the right half plane? And indeed, as we would expect from the theory, it's a sort of straightforward process to bring those over and then destabilize the system. And what's interesting in both cases, we find that the load's participation factor is actually quite low, meaning that with only a little bit of control effort from that active load, that nefarious load, you can destabilize this kind of a system. So thinking ahead then, so first thing we see with this answer to this question, yes, with the right information, we can use this approach that Krista Marco developed a while back for eigenvalue placement to enable either actually stabilization or destabilization. So we showed you a destabilization case, but the idea is you can place those eigenvalues wherever you want. So if you have an unstable system, you can bring them back over into the left half plane. So some work that we're doing right now is to try to relax some of these assumptions about state information and knowledge of the model. So we're looking at options for online model identification with only local information so that you can then adjust the stability with just local information. I've thought about presenting these results today, but decided it was a little bit too early because results could always change. But we have basically is like a prototype power system stabilizer that would sit on board a voltage source converter and do the stabilization that a synchronous generator power system stabilizer would do for these for these lower frequency modes that they typically target, but instead target the faster frequency modes or even these first order modes that we see appearing when we start putting in a lot more voltage source converters. Finally, I just want to reflect on this question about the future of computation and power systems analysis. This is work with my graduate student, Rodrigo Henriquez and Jose Lara, as well as Clayton Barrows, who's a research engineer at National Renewable Energy Lab. So this is a really big effort, and I'm only going to be scratching the surface here. But what I hope I've started to convince you of in the talk today is that there are a lot of complexities that we need to understand on very large spatial scales when we start integrating more and more voltage source converters into transmission systems. So the question that still needs to be answered is, what simplifying assumptions can we continue to make? It looks like we can't continue making simplifying assumptions about things like line dynamics. And so it's looking like we're going to need much more computing capacity for large scale system studies. Furthermore, we're going to need control architectures or flexibility to explore new grid forming control architectures. So as the industry evolves and explores new ideas for how to build the control loops on these devices, we need basically a sandbox for researchers to be able to study the dynamic implications of those different architectures. And so this motivates some computing work that we're doing, in particular to develop a tool that we call Power Simulations Dynamics.jl or PSID. So this is a Julia-based open source computing power system simulation toolbox designed to study these very questions that we're looking at today about system stability, but not only small signal stability, also transient stability, but specifically tailored for questions about low inertia power systems. So we've done a lot of work to put together data models and modularity that facilitate fast model development. So somebody that's interested in testing how their new grid forming control schemes will operate in a large-scale transmission system doesn't have to build a whole new model to do those tests. They can basically pick up off the shelf the tools that we build here, make some simple modifications to a very modular converter control topology to explore those new kinds of control performance. We use this programming language called Julia, which would basically be like an alternative to using something like Python, which many of you have used before, because Julia is right at the cutting edge for solvers for large scale ordinary differential equation solvers, or in particular what we call stiff systems, where we have many different timescales that we need to be concerned about. Julia is also quite exciting from what we call an auto differentiation perspective. So it can do very, very fast differential calculus for Jacobian calculations. It's also a sandbox or a place of enormous development on the much more theoretical sides of machine learning. And so some of the new work that we're starting to do is to leverage the ability that Julia has to do machine learning to accelerate computation. So our vision then is to enable scientific approaching for EMT as electromagnetic transient simulations to study these kinds of emerging questions that we're talking about today. So it enables, as I've suggested, hopefully rigorous study of model complexity versus stability, and also benchmarking different control strategies. And just for a little bit of eye candy here, I've shown this picture on the bottom right, which is comparing the performance of EMT simulation with PSID, the toolbox that we've built, versus PSSE, which is kind of an industry standard tool that you'd use for doing EMT simulations. And in this particular case, you can see that the two simulations just line right up on top of each other. So we've got some at least model-to-model validation with the toolbox that we're building. If you're inclined to do open source computing projects and you're interested in power system dynamics, you can get involved in this project. So we're trying to make this a community of people developing the tools. And we do have a number of different people that are already engaged across several different continents. At a minimum, what we're hoping that people will do is use this tool to do their own dynamic studies and help us flag areas where it needs to be improved. It is working, as that prior slide showed you, but there's a whole lot of development that we'll still surely need to be doing. If you're excited about the project, you can also take part in developing the tools themselves. And the initial way to do that would be to join our Slack channel, which is nrel-sip. So just some closing thoughts, some key takeaways. Our early results, our own as well as a couple of other groups have shown that low inertia small signal instabilities are realistically possible. We believe that we've done some very rigorous study here, but there's a lot more that needs to be done to understand what the future of power systems holds for these kinds of stability events. Very importantly, although we call these low inertia systems, it's not actually the inertia that matters for these instabilities. Instead, it's faster control loop dynamics. We see that in heterogeneous systems, that is synchronous machines plus grid forming converters plus grid following converters. I didn't go deep into these results, but we see actually the most challenging with respect to stability margins problems arising. And what we find is that these stability assessments need to model line dynamics as well as the dynamics of inner voltage and current control loops on converters. This is a level of detail that we have always ignored in stability studies up until now, and it suggests some pretty big challenges with respect to computing scale. And then finally, I think there is a lot of exciting hope. There are a lot of paths to stabilization. And the question is, what should we require of new grid forming and grid following converters? Do they need to solve these problems? Do we need to do it with synchronous machines and grid forming, grid following converters all together, retuning all of their control blocks? Can we solve these problems with some other sort of active load, as I suggested with this attack scenario? Yeah, I think I've just gone through some of these solutions already. But the short story, I think, is a really exciting landscape for thinking about decarbonization of electric power systems at large scales. There's some really exciting dynamic challenges to solve, and there are a number of different paths to get there. And I'm hoping that I will be among a community of many, many people thinking about this in the years to come. So just I've already mentioned these names of people that have helped in this work. We've gotten support from the Department of Energy from a few different venues, as well as funding support from ETH Zurich. And please contact me if you have questions. And I'm right up against 11:30, but I hope some of you can stick around and ask questions if you have them.
Great, thanks so much, Duncan. If there's any questions here, feel free to jump in. It's a lot of good food for thought.
Hi, I had a question. That was a really nice talk. And the results which you had showed for integration of the grid forming and following converters, I just wanted to know if you have any plans to actually test those in real, like a lab kind of prototype, or do you have a big grid like Hawaiian grid or something where you would test out all these theories or the stabilizers which you're talking about in case some adversarial attack happens? Like, what's the roadmap for actually testing out all these cool
This is
results?
a really important question. So in simulation, the roadmap is to a colleague of mine, Brian Mathias Hodge at NREL, and I have worked out some pathways to using a model of the Maui system to explore the kind of emergence of instabilities in those cases. There is, I think, laboratory work to be done. It is not my area, unfortunately. I don't have a hardware lab, and I would be quite eager to collaborate with folks that would. I think some of the most important questions surround what needs to be done with hardware versus hardware in the loop simulation. And I think that we can get some of the way there with the hardware in the loop approach. But ultimately, the thing that I think is going to be very hard to address is what we see so far is that the kinds of modeling assumptions that we're comfortable making in simulation appear to be ones that we can't continue to make. And it's not clear, are there other assumptions that we need, that we've always historically made, that we would naturally make in a hardware in the loop sort of simulation environment that we're not aware of? And so the short answer to your question is, I don't know that there is a really compelling path to validation. And that, I think, is always the challenge with large-scale power systems analysis. But I think that there are some paths to at least get us like inching toward a place where we can feel confident that we can continue operating these systems with a large amount of stability margins.
Thank you. Yeah.
Hi, so I was wondering, is eigenvalue analysis sufficient, and have you considered doing any type of Lyapunov stability analysis for these systems?
I think actually, yeah, the most important additional step I would say is to be thinking about transient stability issues. And that is a direction that we're thinking about going. I think that at the core, the sort of eigenvalue approach is thinking about a kind of Lyapunov stability framework. And so I think we've got the eigenvalue or the small signal stability front covered. There is some interesting, there are some very interesting approaches from power systems analysis that use Lyapunov functions, sort of energy functions, for thinking about system stability. And that is a place where some people, in particular Florian Dorfler's group from ETH Zurich, have explored using those kinds of tools for, especially for designing different kinds of control loops to ensure stability.
Thanks.
Thank you for introducing the grid forming and grid following. Yeah, I'm curious about how the frequency information can be got in the grid forming mode. Yeah, so if they do not need to the PIL block, so does that mean they have some method to directly get the frequency information?
So the frequency set point And I'm anxious giving you this explanation because we have like the world's foremost expert on these online, which is Brian. But so Brian can correct me if I say anything wrong. But the way that I think about it is that the frequency set point, or the frequency, is something that is set on board the converter, right? So the converter has basically a target frequency that it would like to hit, and it also has an associated real and reactive power that it's trying to hit. Now, to the extent that system conditions cause it to diverge from its desired real and reactive power, the converter is going to say, all right, I have a mapping between my desired frequency set point and what I'm actually going to produce as a frequency that maps what I am delivering to the system with respect to real and reactive power to the frequency that I'm actually going to set my converter to operate at. And so the kind of answer to your question is that it's all computed internally, but by the sort of beauty of the way the physics work, this enables power sharing across multiple converters, and they can all actually converge to the same frequency, even if that frequency is different from the set points that they kind of started at the beginning of the day with.
Yeah, and the beauty is you don't have to measure frequency explicitly. It just, you get it for free.
Yeah, so do we got some limits in the frequency? Yeah, for example, in the main grid, we will require that the deviation of the frequency will not too much to avoid it have some negative impact on the loads. Yeah, so do we have this concern for the grid forming mode?
Yes and no. I mean, I think what is it depends a lot on the kinds of gains that we use for the grid forming converter control loops. But if you think about so when you have unstable or sort of large frequency deviations in a system with synchronous generators, those large deviations actually originate from the fact that the synchronous generators are slow to respond. And if you think about the way that a grid forming converter can work, they can be quite fast and reach a steady state frequency after a disturbance very, very quickly. And so the question is, how big is that deviation in frequency in steady state? Even with synchronous machines, that deviation is generally pretty small, or at least not so big that you could cause any kind of damage to loads or cause other devices to trip offline. Ultimately, the main concern for these frequency dynamics is will relays that are designed to trip offline when frequency events get very, very large, that is, if the frequency deviates far enough, some loads will trip offline, other generators will trip offline, essentially to protect themselves. So the question is, can we control the frequency to avoid those large excursions from happening? I would stipulate that that's a much easier challenge when we have less slower rotating machines on the grid that is slow to respond. There's also, I think, other really interesting philosophical questions about whether we should even have those relays that trip devices offline in a world where everything is power electronic converters, because the power electronic converters can operate over a much larger frequency range without any negative implication. And so there are some people that advocate for kind of stopping worrying about frequency in worlds where we have everything kind of interfacing with the grid via power electronic converters.
Yes, thank you very much for the explanation.
Sure.
I have a question to reflect some time. So one of the results that you shared that was pretty cool was the idea that the network dynamics improved the stability of the system. And I was wondering if there was you've also talked about, like, a lot of people have talked about microgrids and keeping like storage and generation local. Is there any is it possible there's any kind of push to adding in simulated network transmission, like some kind of stochastic thing to add in that buffer stability?
I don't think I quite understand the question. That it, yeah.
Adding in a transmission, basically adding in a transmission line seems like it improves the stability of the system. So in a local area, that's not as relevant. Is there a reason, would one way to improve stability be to add in a simulated transmission line?
I see. Oh, that's an interesting idea. Yeah, I think that one of the perhaps an analogy would be, that we actually put like virtual impedances on converters now to try to improve their operations, and so you can kind of basically simulate any kind of physics you would like to kind of trick the converter into doing different kinds of things. So it's an interesting possibility. I think that the questions about line dynamics and stability are going to matter a lot more over long distance scales, though. So if we're just focusing on the kind of microgrid question, I think that those line dynamics are not going to have the same kind of effect. So perhaps what you're saying is, can we simulate kind of long lines in the microgrid? And I don't know, it's an off the wall idea that may actually be one of those ideas that has some legs. It's cool. I'm not sure.
Okay, cool. Well, we're about 10 minutes past here, and I'm thinking here, just for time's sake, unless there's any burning questions and Duncan has time, I think maybe we might just conclude here. Duncan, thanks so much. Really
Thank you all very much. I'm sorry I'm not there in person. Someday, hopefully I will be. Yeah, thanks everybody for joining.
All right, great. Well, take care. Thanks everyone for your time, and we'll go from there.
Okay, bye-bye.